Welcome to Universe Orbit, your gateway to exploring the vast wonders of space, where the mysteries of the cosmos unfold through captivating videos. Don't forget to subscribe so you never miss a single voyage through the infinite universe. Mars has always occupied a special place in the human imagination, a nearby world that glows with reddish promise in the night sky and invites speculation about its secrets. Across millennia, observers on Earth have peered at that ruddy disk and woven myths, prophecies, and hopes. Ancient cultures associated its color with blood and war, while poets and painters treated it as a symbol of otherness and distant possibility. Today, Mars stands at the intersection of science and dream, an object of rigorous exploration by robotic emissaries and a focal point of plans and fantasies about human journeys beyond Earth. The red planet's appeal is not merely aesthetic or romantic. It emerges from a deep combination of scientific curiosity, practical habitability potential, and the practical fact that, among the rocky worlds of the inner solar system, Mars is the most accessible place beyond Earth where humans might one day live. From a distance, Mars appears as a tiny, rusty jewel, but the closer a spacecraft or a human eye through a telescope approaches, the more complex and intriguing it becomes. Its surface is a tapestry of ancient volcanoes, vast canyons, river-carved valleys, dusty plains, and polar caps that wax and wane with the seasons. Olympus Mons rises as a titanic shield volcano, the largest known volcano in the solar system, dwarfing Mount Everest and spanning hundreds of kilometers. Valles Marineris, a canyon system stretching longer than the continental United States, cuts into the crust with steep cliffs and layered deposits that record geologic time. The Martian surface preserves a long, dramatic history written in rocks, a history of violent impacts, volcanic outpourings, surface weathering, and importantly, the sculpting influence of water in a far more temperate era than the present. The red color that gave Mars its popular name comes from iron-rich minerals in the dust and rocks on the surface. When iron oxidizes or rusts, it takes on a reddish hue. Martian dust is ubiquitous and fine, capable of coating spacecraft and darkening solar panels, and it plays a role in the planet's climate by absorbing sunlight and influencing atmospheric circulation. Late afternoon on Mars can show vivid, rusty landscapes beneath a thin veil of ochre haze, while twilight can cast a bluish glow near the setting sun, a subtle reminder that the planet's atmospheric optics are not the same as Earth's. Mars is a cold, dry world by Earth standards. Its atmosphere is thin, mostly carbon dioxide, with surface pressures typically less than 1% of Earth's at sea level. That thin envelope can support weather, including wind-driven dust storms that sometimes swell to encircle the planet, but it cannot retain heat the way Earth's atmosphere does. Surface temperatures vary widely with latitude, season, and local time, swinging between bitter cold at night and modest warmth in the afternoons near the equator, under favorable solar angles. The planet's axial tilt, similar to Earth's, produces seasons. The eccentricity of its orbit amplifies seasonal contrasts in the southern hemisphere, making some southern summers particularly warm. But warm on Mars is relative. Even in the warmest equatorial noon hours, temperatures rarely approach the comfortable ranges humans enjoy on Earth, and the combination of cold, low pressure, and harmful radiation levels creates a hostile environment for unshielded life. Yet despite these difficulties, Mars carries strong clues that, in its ancient past, it was less hostile. The discovery of channels, valley networks, and layered sedimentary rocks points toward a time when liquid water flowed across its surface. Deltas and conglomerates found by rovers and orbiters tell a story of rivers and lakes, perhaps even seas, reshaping landscapes billions of years ago. The chemical signatures in those rocks, minerals that form only in the presence of water, such as clays and sulfates, provide evidence that water was not only present, but came in ways that could have created habitable conditions for microbial life. The timeline suggests that early Mars may have had a thicker atmosphere and a magnetic field that protected it from the solar wind. Over time, that protective layer faded, the atmosphere thinned, and the surface waters either froze, were sequestered as permafrost, or escaped to space. Yet remnants of that watery past remain in the geology, And even today, subsurface reservoirs of water ice are widespread, with massive deposits at the poles and patches of buried ice near the surface at mid and high latitudes. Robotic exploration has been the key to unfolding Mars's secrets. Since the first successful flyby and orbiter missions, humanity has progressively increased its capacity to observe, map, and touch the Martian surface. Orbiters have mapped the planet in exquisite detail, revealing mineralogical maps, topography, and the subtle seasonal dance of the polar caps. Landers and rovers have walked across Martian soil, analyzed rocks with laboratory instruments, sniffed the thin air, and transmitted breathtaking images of alien horizons topped with familiar geological forms. Each mission is an incremental revolution. Early landers measured atmospheric composition and weather. Later missions detected hydrated minerals and complex organic molecules. And modern rovers such as Curiosity and Perseverance have carried sophisticated laboratories capable of detailed chemical and isotopic analysis. Perseverance, in addition to its geological investigations, carries instruments designed to collect and cache rock samples that could be returned to Earth by a future sample return campaign, a prospect that would allow the most intensive analyses by Earth-bound laboratories. The question of life, past or present, on Mars is perhaps the most compelling reason for exploration. Microbial life, if it ever arose on Mars, was most likely at home in environments where liquid water persisted and where energy sources were available. That could include shallow lakes, groundwater systems, hydrothermal vents, or subsurface habitats protected from the harsh surface conditions. The presence of organic molecules detected by rovers is not the same as finding life, because organics can form through abiotic processes. But they raise the stakes. Organics are the raw materials for life as we know it. And when found in rocks that formed in watery environments, they become prime targets for further study. Detecting biosignatures, chemical or morphological traces that unambiguously indicate biological activity, requires careful context-aware analyses. Here, the role of return samples becomes critical, because Earth laboratories can apply technologies and techniques far beyond what is feasible to send on rockets. Even if Mars never hosted life, the story of its climate, geology, and atmospheric loss would still hold profound lessons. Mars is a case study in planetary evolution and the interplay between interior dynamics, surface conditions, and atmospheric escape. Studying how Mars lost its atmosphere and surface water informs our understanding of planetary habitability and the long-term stability of climates. It provides a sobering counterpoint to Earth's own story, emphasizing the delicate balance that sustains a world teeming with life. The processes that stripped Mars of its magnetic field and thinned its air, from large impacts to changes in its core dynamics and the gradual stripping effect of solar wind, are instructive for planetary scientists modeling other worlds, both in our solar system and around other stars. Looking beyond scientific curiosity, Mars represents a tangible destination for human exploration. The idea of sending humans to Mars has moved from pure imagination into the realm of engineering planning and international collaboration. Human missions present extraordinary technical challenges, many of which are unprecedented. The long transit between Earth and Mars, measured in months, requires life support systems capable of sustaining people in microgravity and radiation-filled space for extended periods. The Martian atmosphere, though thin, is thick enough to cause a dramatically different entry, descent, and landing challenge than the Moon, requiring innovative technologies and carefully designed entry profiles. Surface habitats must protect inhabitants from radiation and micrometeorites, provide breathable air, and maintain thermal and pressure stability. Food, water, and energy must either be transported from Earth, which is expensive, or produced in situ, which requires robust and efficient systems for extracting water from ice, producing oxygen from the carbon dioxide-rich atmosphere, and growing food in controlled environments. The concept of in situ resource utilization underpins many plans for sustainable human presence. Mars offers raw materials. Water ice can be converted into breathable oxygen and rocket propellants. Regolith can be used for construction. Atmospherically abundant carbon dioxide can be processed for fuel and chemical feedstocks. Developing reliable and efficient technologies to harvest these resources reduces the mass that must be launched from Earth and makes missions more economically and logistically feasible. Experiments on Earth and on the International Space Station, along with robotic demonstrations on Mars, are steadily increasing confidence that these technologies can work. But many unknowns remain. Subsurface ice may be variably distributed and sometimes inaccessible. Regolith contains chemicals such as perchlораtes that complicate human habitation and agriculture. And Mars's dust is pervasive and abrasive, posing risks to mechanical systems and human health. Human physiology presents another major constraint. Long exposure to microgravity causes muscle atrophy and bone density loss, alterations to fluid distribution in the body, and changes in the immune system. Radiation outside the protective cocoon of Earth's magnetosphere and atmosphere increases cancer risk and can damage the central nervous system. Psychosocial factors, isolation, confinement, and the stress of living in a dangerous environment will test human resilience. Countermeasures including exercise regimes, artificial gravity concepts, radiation shielding using both structural materials and strategically used regolith, and psychological support systems are all being explored. Timing the departure windows to minimize transit time and using missions that incorporate robust abort and contingency plans are part of mission planning. The return journey adds complexity. Any human mission that lands on Mars will need a reliable way to lift off again, which implies either bringing a return vehicle or producing propellant on Mars itself. Terraforming Mars remains the stuff of science fiction and speculative engineering, but it is part of the cultural conversation for a reason. It encapsulates humanity's desire not just to visit, but to reshape and settle new worlds. Ideas range from the technically modest, such as creating localized habitable zones under domes or within underground lava tubes, to the wildly ambitious, like thickening the atmosphere by releasing greenhouse gases or redirecting ammonia-rich asteroids to warm the planet. The practical, ethical, and ecological implications of altering another world at planetary scales are immense. Even if technologically feasible, which is a far from certain proposition, terraforming raises questions about planetary protection, stewardship, and the rights and responsibilities of future generations. If Mars harbors even microbial life, any large-scale modification of its environment would risk destroying an indigenous biosphere. The debate over terraforming therefore forces us to confront the values that should guide our expansion into the cosmos. The search for habitable niches on Mars does not only hinge on grand planetary engineering. Closer to present reality is the potential use of natural shelters like lava tubes. These cavernous structures, formed long ago by flowing lava, could provide substantial protection from radiation and micrometeorites and offer thermal stability. If accessible and structurally sound, lava tubes could be used as sites for human habitats, research stations, or storage and manufacturing facilities. The idea leverages Mars's geology in a pragmatic way, turning natural advantages into shelter. Mapping and exploring these subsurface features with robots is a priority area because it may significantly reduce the technological burden associated with surface living. Mars' cultural and symbolic role cannot be overstated. It is the stage for countless works of literature and film that have shaped public expectations about space travel, from optimistic visions of colonizations to dystopian tales of exploitation and conflict. Those cultural artifacts influence public sentiment and policy, sometimes spurring investment in space programs and inspiring young people to pursue careers in science and engineering. Mars serves as a canvas where humanity projects hopes for discovery, survival, and new beginnings, but also anxieties about imperialism, environmental degradation, and the ethics of expanding our reach. Engaging with these narratives can help shape a more nuanced and responsible approach to exploration. International cooperation and commercial investment are reshaping how Mars exploration is organized and funded. Space agencies from different nations collaborate on scientific missions, sharing data and resources to increase overall capability. At the same time, private companies are developing launch systems, landers, and propulsion technologies that could lower the cost of access to space and accelerate timelines. The interplay between public sector mission planning, with its emphasis on science and long-term research goals, and private sector ambitions, sometimes driven by shorter-term commercial objectives, creates both opportunities and frictions. A durable human presence on Mars will likely require diverse partnerships that combine governmental authority and oversight, scientific priorities, commercial agility, and international legal frameworks to manage the complex social and political dimensions of off-world settlement. Ethical considerations are central to responsible exploration. Planetary protection policies aim to prevent forward contamination, the introduction of Earth microbes to Mars, and backward contamination, the risk of returning potentially hazardous Martian material to Earth. These policies are not mere bureaucratic hurdles. They are rooted in caution and responsible science. Protecting the integrity of scientific investigations means avoiding contamination that could obscure evidence of past or present life. Protecting Earth from unknown biological hazards is equally important. As exploration intensifies and human footprints expand, maintaining rigorous contamination controls will be challenging, but essential. Ethical debates also extend to property rights, resource use, and governance. Who gets to settle Mars? Under what rules? And how will the interests of future generations be safeguarded? Technological advances continue to open new possibilities. Improvements in propulsion, from more efficient chemical rockets to concepts for nuclear thermal or electric propulsion, can reduce transit times and increase payload capacity. Advances in robotics and autonomy let landers and rovers explore more complex terrains and perform intricate scientific tasks with minimal real-time guidance. Additive manufacturing, or 3D printing, offers the potential to create tools, components, and even structures from local materials, reducing dependence on Earth-supplied parts. Life support systems are becoming more efficient at recycling air and water, and agricultural technologies for closed-loop bioregenerative systems are making slow but steady progress. Each of these incremental advances compounds, bringing the vision of human Mars missions into sharper relief. Public engagement and education form an essential bridge between the technical community and the society that ultimately funds and supports exploration. Mars missions capture the public imagination because they are tangible and evocative. They promise dramatic vistas, the search for life, and the possibility of human footprints on alien soil. Outreach that communicates the scientific objectives, the risks, the costs, and the ethical context is crucial for building sustained support. At the same time, engaging artists, writers, philosophers, and diverse cultural voices helps ensure that exploration is not just a technical endeavor, but a humanistic one, reflecting a wide range of perspectives about why we go to the stars and how we ought to behave when we get there. Mars will continue to surprise and instruct us. Each layer of rock we probe, every molecule we identify, and each meter of terrain a rover traverses adds data to a long story that stretches back billions of years. The planet is a laboratory for understanding planetary habitability, a proving ground for technologies required to live off Earth, and a mirror that reflects our deepest ambitions and anxieties. The roadmap to human exploration is strewn with hurdles: engineering unknowns, physiological limits, political and economic constraints, and ethical quandaries. But the reasons to persist are compelling. Scientific knowledge grows not only for its own sake, but also because the techniques and technologies developed for space exploration often find beneficial applications on Earth. From advanced materials in remote sensing capabilities to medical technologies in sustainable life support systems. The dream of Mars evokes the thrill of discovery and the necessity of humility. We approach with instruments honed by decades of learning, and with a cultural repertoire shaped by literature and film, by poetry and policy debates. We must also recognize the limits of our knowledge and the responsibility that comes with cosmic reach. The search for life, the pursuit of sustainable human presence, and the dialogue about how to govern and protect off-world environments are all exercises in collective wisdom. They ask us to balance curiosity with caution, to weigh immediate gains against long-term stewardship, and to imagine futures that respect the intrinsic value of other worlds. As we look ahead, we might imagine a cascade of milestones. More advanced robotic scouts mapping subsurface ice, sample return missions delivering pristine Martian material to Earth laboratories, demonstration projects for in situ resource utilization that produce oxygen and fuel, and eventually human missions that set foot on ancient riverbeds and sleep beneath engineered domes or natural lava tubes. Each step will expand our understanding and refine our ability to live beyond Earth. Equally important will be the conversations we hold about the ethics of exploration, the legal frameworks that evolve, and the cultural narratives we build. Mars remains, in essence, a distant relative, familiar enough to spark concrete plans, always enough to demand humility. It invites questions that are scientific, practical, moral, and philosophical. Are we content to witness another world from afar, or will we become its inhabitants? If we take residence, how will we treat a world that might contain traces of a separate origin of life? If we do not find life, what does that tell us about the rarity or resilience of living systems? In grappling with these questions, we learn not only about Mars, but about ourselves. The red planet is a teacher that forces us to confront the fragility of habitable environments, to value the unique conditions that sustain life on Earth, and to imagine how human ingenuity and responsibility might combine to explore the cosmos without repeating the mistakes of the past. The story of Mars is still being written, with chapters unfolding through beeps from orbiters, rolling wheels of rovers, and the plans sketched by engineers and dreamers. It is a saga of natural history and human aspiration, of rock and rust and riverbeds frozen in time, of laboratories housed in boxes that cross millions of kilometers to touch alien soil. As our tools become more refined and our reach extends, Mars will remain both a scientific objective and a symbol, a place where knowledge and imagination meet, and where human dreams of exploration continue to propel us into the vastness beyond our blue planet. Mars offers a stage on which humanity rehearses its future, and as we continue imagining what that future might look like, the planet grows richer in meaning. To extend the journey, one must dive even deeper into the intertwined themes of science, engineering, culture, and the human spirit that shape our relationship with the red planet. The very act of contemplating a world so different from Earth stretches our imagination and compels us to consider what it truly means to be a species capable of altering its destiny and expanding beyond its birthplace. In this extended exploration, the story of Mars becomes not only more detailed, but more human, revealing the full spectrum of challenges and aspirations that accompany the dream of reaching another world. The contradictions and dualities of Mars are central to its allure. It is close yet far, familiar yet alien, inviting yet hostile. This duality creates a psychological tension that stokes both fear and excitement. Standing on Mars would feel bizarrely similar to standing in a remote desert on Earth. Dusty ground beneath your feet, rocks strewn across the landscape, a horizon shaped by hills and mountains. Yet the sky above would be tinted a faint but unmistakable salmon hue, the air unbreathably thin, the cold biting, and the silence absolute. The sun would appear smaller, casting elongated shadows across the barren plains. Each sunrise and sunset would resemble a ghostly inversion of Earth's palette, with sunsets tinged in blue as Rayleigh scattering behaves differently in the dust-laden Martian air. The combination of familiarity and alien strangeness is perhaps the most visceral and haunting characteristic of Mars. The planet's surface carries the scars of ancient disasters and quiet eons. Impact craters of all sizes punctuate the landscape, some weathered and softened by time, others sharp-edged and young. In certain regions, craters are so densely packed that they paint a picture of an early solar system filled with violent collisions. But in other regions, fewer craters suggest more recent geological resurfacing, often related to volcanic or fluvial activity. This patchwork of epochs allows researchers to reconstruct Mars's past, teasing out clues from the distribution of crater densities, the layering of sedimentary beds, and the mineral signatures detected from orbit. The story that emerges is one of transformation, a warm, thicker atmosphered Mars slowly cooling, drying and fading into the desert planet we see today. The magnetic field once generated by Mars's core played a vitally important role in its early climate. A strong magnetic field shields a planet's atmosphere from the charged particles streaming from its star. When Mars's internal dynamo shut down billions of years ago, the protection waned and the atmosphere began to escape into space, stripped away slowly but relentlessly by solar wind. Over eons, The thinning atmosphere became too weak to maintain surface pressure capable of supporting stable liquid water. This atmospheric loss is not just a geological curiosity, it is central to any discussion about habitability. If life ever existed on Mars, it would likely have needed protection to survive the loss of this atmospheric barrier, retreating underground or into isolated pockets where conditions remain stable. Scientists continue to debate how long Mars could have sustained habitable environments. Some climate models propose long-standing oceans in the northern lowlands. Others argue for intermittent lakes and streams driven by episodic warming events, such as volcanic eruptions or asteroid impacts. The search for ancient shorelines, for buried sediments beneath the northern plains, and for fossilized microbial mats in ancient lake beds fuels ongoing missions. Even without definitive proof yet, the patterns observed in river deltas, particularly those explored by Perseverance in Jezero Crater, are strongly reminiscent of deltas on Earth, where life thrives. Rocks that formed in calm, watery environments are precisely the archives planetologists hope to decipher. In the modern era, exploration of Mars has become a global endeavor. The fleet of spacecraft studying the planet includes orbiters from multiple nations, each contributing to a composite view of the planet's climate, geology, and surface composition. The ceaseless stream of data allows researchers to refine models and detect subtle changes, such as seasonal carbon dioxide frost accumulating on dunes, water ice clouds drifting over volcanic peaks, or shifting patterns in dust storms. Long-lived rovers act as field geologists with mechanical patience, crawling through craters and ridges to drill rocks, take microscopic images, and fire lasers at outcrops to determine their chemical composition. The engineering triumphs involved in landing these robots on Mars are remarkable. Every successful mission is a testament to meticulous design and innovation. Mars's thin atmosphere makes parachutes less effective, yet dense enough to generate intense heat during entry. Engineers have developed ingenious combinations of heat shields, supersonic parachutes, retro rockets, and even the famous sky crane system that lowered the Curiosity and Perseverance rovers onto the surface with cables. A dramatic maneuver that has since become one of the most iconic examples of planetary landing technology. Each landing is a high-wire act with no room for error and no possibility of intervention once the spacecraft begins its descent. Modern missions increasingly incorporate autonomy. Communication delays between Earth and Mars range from several minutes one way, making real-time remote control impossible. Rovers must make many decisions on their own, from obstacle avoidance to instrument calibration. Future missions may rely even more heavily on AI-enhanced systems capable of identifying areas of scientific interest, navigating complex terrain, or performing maintenance tasks that would be routine for humans but are difficult for machines. As the body of knowledge about Mars grows, so too does the sophistication of human mission proposals. Engineers envision multi-stage mission architectures, beginning with orbital reconnaissance and cargo delivery, followed by automated construction of support infrastructure, and culminating in crewed missions. The sequence might start with robotic landers delivering power systems, habitats, fuel production plants, and scientific equipment. These systems could operate autonomously for years before the first human crew arrives. When humans do land, they would ideally find a functional outpost producing oxygen, storing water, generating power, and offering a safe refuge. A challenge that remains at the forefront of planning is radiation. Mars's thin atmosphere and lack of a global magnetic field expose the surface to high levels of cosmic rays and solar radiation. Shielding solutions include burying habitats beneath regolith, constructing habitats inside lava tubes, or integrating materials like polyethylene or hydrogen-rich compounds into structural walls. Water itself serves as an excellent radiation shield, and some habitat concepts propose surrounding crew quarters with tanks of water or ice. With time, researchers anticipate developing more advanced materials capable of blocking or deflecting harmful radiation while remaining lightweight, a key requirement for off-world construction. Psychological resilience is another essential element of human Mars missions. Astronauts will be separated from Earth by millions of kilometers, with communication delays that eliminate the possibility of real-time conversation. They must operate within confined spaces, maintain calm under stressful conditions, and sustain teamwork through long periods of monotony, punctuated by moments of danger. Simulated Mars habitats on Earth, in deserts, Arctic regions, or specially designed research stations, attempt to replicate some of these challenges. They offer insights into crew cohesion, resource management, and the ergonomics of isolated living. But no simulation can perfectly emulate the profound reality of living on another planet. The knowledge that returning home is not a quick decision, but a complex interplanetary maneuver that can only occur at specific alignment windows every 26 months. In addition to human factors and life support concerns, Mars settlements must also navigate the complexities of planetary law. The Outer Space Treaty forbids nations from claiming sovereignty over celestial bodies, but it remains ambiguous about resource extraction and long-term settlements. As commercial and national interests converge on Mars, the international community will need frameworks that address property rights, environmental protections, and conflict resolution. The development of space commons policies, inspired by maritime and Antarctic treaties, may shape how Mars is shared, explored, and used. Another dimension to the future of Mars exploration involves scientific instruments of unprecedented precision that one day could be part of a permanent laboratory on Mars. A base staffed by scientists could perform experiments impossible or inefficient with robotic missions alone. They could conduct deep drilling operations to reach layers untouched for billions of years, excavate samples from protected subsurface ice deposits, or deploy sensitive seismometers in radar systems across wide networks. Such a scientific settlement would transform Mars from a distant research target into a fully fledged extraterrestrial field station. Research conducted on Mars could also inform new technologies beneficial to Earth. Experiments in agriculture and sustainable energy under harsh conditions might yield innovations in drought-resistant crops, efficient recycling systems, or advanced solar power technologies. Studying extremophile microbes, if any exist on Mars, could revolutionize biotechnology, medicine, and our understanding of the limits of life. Even if no Martian life exists, experiments involving Earth microbes in controlled Martian analog environments could reveal insights into resilience, DNA repair, and microbial adaptability. For many scientists and thinkers, the philosophical implications of Mars loom just as large as the scientific ones. The presence or absence of life on Mars represents a profound fork in our cosmic narrative. If Mars never developed life, despite having water and many of the ingredients necessary for habitability, then life might indeed be rare, a fragile and improbable spark. If Mars once hosted microbial life that later died out, it would demonstrate how precarious habitability can be. And if Mars still hosts life, perhaps underground or in briny subsurface pockets, it would force us to confront the reality of a second genesis. Such a discovery would revolutionize biology, forcing a reevaluation of life's definition, its universality, and the possibility that life is common throughout the universe. Beyond the scientific and philosophical aspects, Mars also inspires practical dreams. People envision farms in geodesic domes producing leafy greens under artificial lights, workshops manufacturing tools from local metals, greenhouses warmed by geothermal heaters, and children born and raised under the pink-tinted Martian sun. These images belong partly to science fiction, but increasingly reflect serious speculation in space architecture and long-term mission planning. The psychology of building a community on Mars involves grappling with questions of identity, culture, and meaning. What traditions would arise? What languages would evolve? How would the concept of home change for generations who grow up never having seen Earth with their own eyes? The growth of a Martian society would depend heavily on how well it maintains sustainable systems. Closed-loop life support, efficient recycling, robust energy grids, and modular habitats that can expand as the population grows are key elements of settlement design. Renewable energy, primarily solar, supplemented perhaps by nuclear reactors, would power everything from oxygen generators to scientific equipment, Water production and conservation would be paramount. Ice mining might become a major industry. Over time, advanced manufacturing plants capable of producing plastics, metals, electronics, and building materials from Martian resources could allow a settlement to become increasingly independent from Earth. Mars would likely develop its own economy, at least in miniature. Early on, the most valuable export would be scientific data and knowledge. Later, manufacturing in low-gravity environments might produce materials with unique properties. Mars might one day supply propellant for missions headed further into the solar system, using its water ice to create hydrogen and oxygen fuel. The planet could become a gateway to the asteroid belt, serving as a logistical hub for mining and exploration. Culturally, Mars may become a crucible for new art, music, and storytelling traditions. Artists might express the stoic beauty of Martian landscapes, the smooth flanks of giant volcanoes, the jagged edges of eroded cliffs, the delicate frost patterns that appear at dawn. Writers might explore the emotional experience of living so far from Earth, blending themes of isolation, community, discovery, and reinvention. Over generations, a unique Martian identity would likely emerge, shaped by the environment and the challenges of life on a frontier world. These cultural developments highlight one of the most profound aspects of the human relationship with Mars. It pushes us to re-examine what civilization means when transplanted to another world. On Earth, geography, climate, and ecosystems shape society. On Mars, the environment would shape it even more strongly. Every aspect of life, from agriculture to architecture, from education to recreation, would be constrained and guided by the Martian environment. As this vision unfolds, the story of Mars becomes not merely scientific exposition, but a narrative of transformation. The journey from robotic exploration to human settlement is a multi-generational undertaking that challenges our technological capabilities, economic structures, ethical principles, and imaginative horizons. The dream of Mars is not solely about reaching a planet, it is about expanding the possibilities of human experience. Mars calls to us because it offers a canvas on which to paint new futures, a mirror through which to examine ourselves, and a laboratory in which to test our most daring ideas about survival and exploration. It stands as both destination and symbol, a place of red dust and ancient secrets, and a frontier where human ingenuity and curiosity may one day carve out a new chapter in our species' long story. Beneath the surface of Mars lies a realm that holds perhaps the greatest promise for future discovery, the subsurface. Buried beneath meters or kilometers of regolith and rock, ice deposits preserve both water and clues to the planet's past. Radar instruments from orbiters have revealed thick sheets of water ice near the poles and mid-latitudes, sometimes buried beneath a thin layer of soil, other times concealed beneath more substantial rock strata. These frozen reservoirs are not merely scientific curiosities, they represent critical resources for human exploration, providing water for drinking, oxygen production, and even fuel manufacturing through electrolysis. The distribution of subsurface ice also raises questions about Mars's climatic past, indicating periods when ice accumulated more widely, hinting at dynamic cycles of glaciation and thaw. The possibility of life in the subsurface has fueled both imagination and investigation. Shielded from harmful radiation, with stable temperatures and potential access to liquid brines, these underground niches could be havens for microbes if life ever arose on Mars. Modern missions and future drilling efforts aim to penetrate these icy layers to search for organic molecules, biosignatures, or microbial relics. Understanding whether life exists or once existed beneath Mars's surface would revolutionize biology, offering a second data point for understanding life's resilience beyond Earth. It would also profoundly influence how humans approach the ethical considerations of settlement and resource extraction, emphasizing stewardship of a potentially living world. Human survival on Mars hinges on technology that can transform the harsh environment into a livable habitat. Life support systems must recycle air and water efficiently, manage waste, and provide protection from radiation and temperature extremes. Innovations in energy generation are central. Solar panels must cope with dust accumulation, while nuclear or hybrid power systems provide reliable alternatives for prolonged operations. Habitat design is increasingly innovative, incorporating inflatable modules, 3D printed structures from local regolith, and underground facilities to leverage natural insulation. The integration of robotics with human operations allows for remote maintenance, construction, and scientific work, reducing the physical burden on crew members and expanding the range of tasks possible. Food production is another critical frontier. Carrying enough provisions for months-long missions is impractical, making in-situ agriculture essential. Controlled environment greenhouses can grow vegetables and fruits using hydroponics, aeroponics, or soil substitutes. Advanced LED lighting tailored to plant photosynthetic needs, closed-loop water systems, and nutrient recycling allow for efficient growth in confined spaces. Scientists are also investigating how Martian gravity, lower than Earth's, affects plant development and nutrient absorption, insights that will shape the design of agricultural modules. Beyond sustenance, food production contributes to psychological well-being, giving crews a tangible connection to life and growth in an otherwise barren landscape. Terraforming Mars remains a distant, speculative possibility, yet it illustrates the scale of human ambition. Conceptual schemes include thickening the atmosphere to trap heat, releasing greenhouse gases to warm the planet, or redirecting volatile-rich asteroids to supplement the air. Each proposal is rife with technological and ethical challenges. The energy requirements for planetary-scale engineering are astronomical, and the environmental consequences unpredictable. If microbial life exists, large-scale terraforming could destroy it. These debates force humanity to consider the broader implications of planetary modification, emphasizing that exploration carries responsibility and that the awe-inspiring dream of reshaping worlds must be tempered with caution and respect. Mars also demands profound psychological and social adaptations from its explorers. Isolation, confinement, and the omnipresent knowledge of danger will shape human behavior. Crew members must cultivate resilience, strong teamwork, and self-sufficiency. Psychological support systems may include virtual reality experiences replicating Earth environments, communication delays requiring autonomous decision-making, and structured routines to maintain mental health. Over longer periods, social structures, cultural practices, and governance frameworks will develop, reflecting a new human experience shaped by Martian conditions. Communities on Mars will likely innovate forms of art, ritual, and social organization unique to their environment, creating a cultural identity that intertwines with the planet's landscape and challenges. Governance, law, and ethics on Mars present complex challenges. International treaties currently regulate space activities, but permanent settlements will require new frameworks to manage property rights, resource use, environmental protection, and conflict resolution. Balancing national interests, private enterprise ambitions, and scientific priorities will be crucial. Ethical considerations include planetary protection, ensuring that human activity does not irreversibly contaminate potential Martian ecosystems. Decisions made now will shape the trajectory of human presence for generations, demanding foresight, cooperation, and a commitment to sustainable, responsible exploration. Mars's role in human culture and imagination remains profound. Literature, film, and art have portrayed it as both a perilous frontier and a realm of boundless opportunity. From early pulp fiction, imagining Martian civilizations, to modern cinematic visions of colonization and survival, these narratives shape public perception and inspire generations to study science and engineering. Mars represents a mirror of human ambition, fear, and creativity, reminding us that exploration is as much about our inner world as it is about distant planets. Scientific discovery on Mars will likely accelerate with human presence. Astronaut scientists could perform complex analyses, conduct controlled experiments in situ, and explore terrains inaccessible to rovers. Deep drilling, large-scale geophysical surveys, and comprehensive sampling could unlock secrets of Mars's climate history, geological evolution, and potential biological activity. Insights gained will enrich planetary science and inform strategies for living sustainably on Earth and beyond. Mars is also a stepping stone to the broader solar system. Knowledge, infrastructure, and technology developed for Mars missions will support endeavors to explore asteroids, moons of Jupiter and Saturn, and eventually exoplanets. Mars's proximity makes it an ideal proving ground for life support systems, habitat design, and interplanetary logistics. It offers a bridge between Earth-bound civilization and a future in which humanity inhabits multiple worlds, testing our capacity for adaptability, innovation, and cooperation. In education and public engagement, Mars inspires curiosity and learning. Its exploration engages students in STEM disciplines, fuels interest in robotics, engineering, biology, and environmental science. Interactive experiences, simulations, and media coverage provide a tangible connection to space exploration. Public enthusiasm translates into political and financial support for missions, creating a feedback loop where fascination with the red planet fuels both scientific and cultural progress. The red planet remains a beacon of discovery, challenge, and aspiration. Its deserts, canyons, volcanoes, and polar caps tell a story billions of years old, yet it is still writing new chapters through human and robotic exploration. The interplay of geology, climate, potential biology, and human ingenuity creates a dynamic narrative that spans the scientific, practical, ethical, and imaginative domains. Each mission, instrument, and sample collected brings us closer to understanding Mars, revealing both its differences from Earth and its resonances with our own planet. Ultimately, Mars embodies the dual nature of exploration. It is both an external frontier of science and an internal frontier of human capability. It tests our technology, our endurance, our ethical frameworks, and our imagination. It challenges us to think on a planetary scale while remaining acutely aware of the fragility of life. The Red Planet calls humanity not only to visit, but to learn, adapt, and reflect, offering lessons about resilience, curiosity, and the responsibilities that accompany expansion into the cosmos. The dreams Mars inspires are as tangible as they are visionary. They encompass the thrill of discovering ancient riverbeds, the hope of uncovering evidence of life, the technical mastery required to land safely and survive, and the philosophical questions about our place in the universe. Mars represents a convergence of past, present, and future, an ancient world that preserves the record of planetary evolution, a present-day laboratory for robotics and human ingenuity, and a potential home for generations yet to come. It challenges humanity to transcend its limitations, to collaborate across nations and disciplines, and to imagine futures that honor both the planet and our shared responsibilities. Through careful planning, scientific rigor, and ethical foresight, humanity may one day walk on Mars, study its ancient rocks firsthand, and live beneath its alien skies. Each step taken on the Martian surface will be a milestone, not just in exploration, but in the ongoing story of human curiosity, creativity, and courage. Mars is more than a destination. It is a mirror reflecting our dreams and a proving ground for our collective ingenuity. The Red Planet, ever distant yet tantalizingly close, invites us to expand the horizon of human possibility, to dream boldly, and to journey wisely into the broader cosmos. Mars, in all its stark beauty and scientific intrigue, continues to shape human imagination and ambition in profound ways. Beyond the immediate goals of exploration and settlement, it offers a long-term vision of humanity as a multi-planetary species. The very idea of humans living on Mars challenges conventional notions of civilization, society, and identity. Unlike Earth, where abundant resources and familiar climates allow for relatively unconstrained development, Mars imposes strict limitations that will shape every aspect of life, from daily routines to governance structures, from social norms to artistic expression. Life on Mars would require constant innovation, careful planning, and a collective commitment to sustainability, forcing us to rethink how communities can thrive in extreme and isolated environments. Education and scientific research on Mars would evolve in unique ways. Young scientists raised on Mars would grow up in an environment shaped by its physical and technological constraints, gaining firsthand experience with planetary science, robotics, and environmental management. Their worldview would naturally differ from Earthbound perspectives, likely emphasizing interdependence, adaptability, and respect for natural systems. This new generation could drive breakthroughs not only in space exploration, but also in technologies applicable to Earth, particularly in resource efficiency, climate adaptation, and closed-loop life support systems. Mars also offers a laboratory for understanding human psychology and sociology under extreme conditions. Long-term isolation, dependence on technology, and the awareness of living in a hostile environment will create pressures unlike any faced on Earth. Social structures, conflict resolution strategies, and community norms will have to evolve to maintain cohesion, resilience, and mental health. This environment may produce novel approaches to governance, collaboration, and cultural expression, offering insights that could inform life on Earth and future off-world settlements. The lessons learned could shape not only space policy, but also approaches to managing isolated or extreme communities here at home. Culturally, Mars will inspire new forms of art, literature, music, and philosophy. The unique landscapes, towering volcanoes, expansive canyons, vast deserts, and shifting dust storms will influence creative expression, just as the extreme conditions and profound isolation shape narrative themes. Martian culture may explore ideas of human fragility, technological reliance, adaptation, and the confrontation with the unknown. Over generations, a distinct Martian identity may emerge, blending Earth heritage with the realities of life on a new world. This cultural evolution will be inseparable from the physical and scientific realities of the planet, intertwining imagination, survival, and innovation. Ethical considerations will remain central to the human relationship with Mars. Decisions about resource use, planetary protection, environmental modification, and the potential discovery of life carry profound moral weight. Planetary protection guidelines seek to prevent contamination, preserving both the scientific integrity of Martian investigations and the integrity of Earth itself. Beyond microbial concerns, the ethical framework must address human settlement, governance, and the long-term sustainability of a Martian society. Humanity will need to balance ambition with responsibility, ensuring that exploration and colonization do not replicate past mistakes made on Earth in exploiting and damaging environments. Economically, Mars may develop unique industries that reflect its environment. Early economic activity will likely focus on scientific research, resource extraction, and supporting the settlement infrastructure. Over time, advanced manufacturing, energy production, and possibly interplanetary transport could become significant economic drivers. The low gravity and unique conditions may allow production of materials or technologies that are difficult or impossible to produce on Earth. Mars's role as a logistical hub for further solar system exploration could transform it into a critical node in humanity's expanding interplanetary network. Scientific knowledge gained on Mars will extend far beyond the planet itself. Studying Mars's geology, climate, and potential biology informs comparative planetology, helping us understand Earth's history and evolution. The processes that shaped Mars, volcanic activity, water loss, atmospheric thinning, provide insight into planetary habitability and long-term climate dynamics. These lessons are crucial for understanding the future of Earth, particularly in the context of climate change, resource management, and environmental stewardship. Mars becomes both a mirror and a laboratory, reflecting lessons about resilience, adaptation, and the fragile balance required to sustain life. Mars's role in shaping human aspiration cannot be overstated. Its reddish glow in the night sky has fascinated humanity for millennia, inspiring myths, stories, and dreams. In modern times, the planet has become a tangible destination, offering both scientific and practical challenges. The combination of proximity, potential resources, and historical intrigue makes Mars a uniquely compelling target for exploration. It embodies the human drive to venture into the unknown, to test limits, and to expand the realm of experience and knowledge beyond Earth. In the long-term vision, Mars may serve as a stepping stone to the wider cosmos. The experience gained in exploring, surviving, and potentially settling Mars will prepare humanity for journeys to more distant destinations, the moons of Jupiter and Saturn, the asteroid belt, and eventually exoplanets orbiting other stars. Each success on Mars builds confidence in our ability to live off Earth, manage complex systems in alien environments, and sustain human culture and knowledge across vast distances. Mars thus represents both a goal and a training ground, bridging the gap between our earthly origins and a future that stretches across the solar system and beyond. The dream of Mars continues to evolve, fueled by scientific discovery, technological innovation, and the unyielding human spirit. It encompasses rigorous research, daring engineering, ethical reflection, cultural creation, and philosophical inquiry. The Red Planet challenges humanity to think on multiple scales: the local and the planetary, the immediate and the generational, the scientific and the existential. Each robotic mission, each instrument, and each future human exploration will add to our understanding, not only of Mars, but of ourselves, our capabilities, and our responsibilities as a species capable of reaching across space. Mars embodies the duality of exploration. It is both an external frontier and an internal test. It demands mastery of technology, insight into human psychology, ethical deliberation, and the ability to imagine futures that are sustainable, equitable, and inspiring. The planet's ancient rocks, frozen ice, vast deserts, and towering volcanoes offer a record of cosmic history and a canvas for human endeavor. In studying Mars, humanity confronts the limits of knowledge, the fragility of life, and the possibilities for creating new worlds, new societies, and new experiences. The Red Planet challenges us to combine curiosity with caution, ambition with responsibility, and imagination with practicality. In this ongoing journey, Mars remains both destination and symbol. It is a scientific laboratory, a proving ground for human survival, a must for culture, and a mirror for self-reflection. It represents the interplay of past and future, nature and technology, earthbound heritage and extraterrestrial possibility. Each discovery, each technological breakthrough, and each ethical debate enriches our understanding, shaping the path toward human presence beyond our home planet. Mars invites humanity to dream boldly, explore responsibly, and imagine expansively, offering lessons that resonate not only in space, but in the choices we make on Earth. Through this enduring engagement with Mars, humanity gains more than knowledge of rocks, ice, and atmosphere. We gain insight into resilience, innovation, and the profound connections between environment, life, and society. The Red Planet's deserts and canyons, dust storms and polar caps, frozen water and ancient riverbeds form a rich tapestry for both exploration and reflection. Mars calls us to extend our reach, expand our understanding, and contemplate our responsibilities. To the planet itself, to future explorers, and to the broader cosmos that awaits beyond our skies. Mars, ever red and ever distant, stands as a testament to human curiosity and aspiration. Its mysteries beckon, its challenges test, and its possibilities inspire. Whether through robotic emissaries pioneering human explorers or the unfolding story of long-term habitation, the Red Planet continues to shape the trajectory of science, technology, culture, and imagination. It is a world of contrasts, harsh yet beautiful, forbidding yet inviting, a place where knowledge and dreams converge, where human ingenuity and courage are measured, and where the future of exploration takes shape. In our pursuit of Mars, we confront not only the unknown of a distant world, but also the boundless potential within ourselves, forging a path toward a future where humanity is truly a species of the stars.